So today we are testing a proportion P. This is section 8.3, which once again deals with hypothesis tests. So we are switching from testing means, which is what we were doing in 8.1 and 8.2, and now we're going to test proportions or percentages. Really, it's the same thing. So this will be a little bit like section 7.3. So recall from section 7.3 that for large samples, and we define large samples by this, meaning that these two conditions are met, right? Just like 7.3, n times p is greater than 5 and n times q is greater than 5. And when that happens, the distribution of these p hat values, remember p hat is just r over n. R is the number of successes, n is the number of trials. These are from a binomial distribution, so a lot of times, if you remember, we'll have a proportion. So let's say this is the population proportion of voters who are going to vote yes on proposal 3, whatever that is. We want to know what proportion of voters are going to vote yes on proposal 3. So what we do is we take a sample, and maybe we get p hat equals 0.72. So this is our sample statistic. In this case, it's our sample proportion. And we're going to use this sample proportion, to try to infer things about the population proportion. So, just to kind of recall from 7.3. So once we know that we have these large samples, then the distribution of these p hat values is approximated by the normal distribution. So in other words, if we took a bunch of these samples, we wouldn't expect them to all be the same. So this one, the sample proportion was 0.72 or 72%. Maybe we take another sample, we get 68% or 0.68. But if we kept doing that and lined up all of these samples, we'd get a nice bell-shaped curve because these samples of p hats would be a normal distribution as long as these two conditions are met. And it'd be a normal distribution with a mean of p and the standard deviation sigma, which would be the square root of p times q over n. Now remember, q is just 1 minus p. Right? It's a binomial distribution, means there's two outcomes. Did you vote yes on, or will you vote yes on proposal 3? Yes or no, those are the two outcomes. So p plus q has to be 1. So for these hypothesis tests for p, the null hypothesis will be p equals some number k. So just like before, our null hypothesis will always be equals. But look at, now we don't have mu, we have p, right? We're testing for p. So part of hypothesis test is paying attention to what the details are. This is testing for p, the population proportion, not for mu. We don't care about sigma. We don't care about the mean. We're talking about population proportion p. And this will be some number between 0 and 1, right? Maybe we believe p is 0.43 or 43%, right? So it'll be a number like that. So the alternate hypothesis, there are 3 possible, the same as before. There are 3 possible, and we will pick one of these based on the situation. And for us, our book will tell us which one to go with. But there are 3 possible. So just like before, there are 3 possible alternate hypotheses. And they all have this same look. Remember, h sub 0 is a null, h sub 1. Or you could say h sub a, right? That's the other way to write this. So we could have p is less than k, p is greater than k, or p is not equal to k. Just like before. So this one is a left-tailed test. This is a right-tailed test, and this is a two-tailed test, just like before. This example we're going to look at, we're going to consider the two-tailed test. So I'm going to make a note of this. This is a two-tailed test. Also, the note here says p is a probability. It's a probability, right? Or a proportion. so that K is going to be between 0 and 1. Right, so this K right here has to be between 0 and 1. You can't have, like if we're trying to guess the population proportion of voters who are going to vote yes on proposal 3, we can't say 2. That doesn't make any sense, right? The proportion is got to be between 0 and 1, right? Like if 50% of the voters, that's 0.5. If 100% of them, that would be, if 100% of the voters are going to vote yes on proposal 3, this would be 1, right? 1 is a decimal, or 100%. So it's got to be between 0 and 1 for this number K that we set P equal to. Then we've got our Z-score from our sample test statistic. You know, this is a little different, but the key to notice this is a Z-score, right? We're going to use a standard normal distribution. Standard normal. Remember, whenever proportions are involved, we're using standard normal. And another thing that's going to be a little bit different. So, if you guys remember in section 7.3, if you guys remember in section 7.3, we didn't know P, right? We didn't know the population proportion. We were trying to estimate it based on P hat. But in section 8.3, we actually know it. So we're going to use P because P will be given in the null hypothesis. So in section 8.3, we know P because it's given in the null hypothesis, right? So it's given in the null hypothesis. So that's one of the differences. We're actually going to know what P is, or at least what we believe it to be. So that'll be different. So when we use this, we actually plug in P. So this is P hat from our sample, right? That's our sample test statistic, P hat. And then this will be P from the null hypothesis. This is the same P, right? If the null hypothesis is P equals 0.4, that P and that P are the same. And then Q, of course, is 1 minus P, and N is the sample size. So there's something really important, though, for us, and that is to read this. So sometimes I mention, like, maybe read this little blurb here, and it'll make things more clear. This is really important. You really want to read this. It just gives some good information there, and it's, a page and a half, so it's not too much to read, but it is very good information, and you'll be better off if you read that. So, all right, we've got a problem to try, and it's very closely related to everything we've done in Chapter 8. It's just another hypothesis test, but it's with a different situation. So in this case, you're doing them with proportions. So looking at the problem here, it says in a 2011 National Institute on Alcohol Abuse and Alcoholism survey, 33% of American adults said that they had never consumed alcohol. So then it says, suppose that this result is true for the 2011 population of American adults. So in other words, suppose this is true. So this may have been a very large study, and people feel very confident in the results. So we're sort of assuming this is true. So this is going to be part of our H naught. It's our null hypothesis. We're assuming this is true. Right? So our null hypothesis will be that P equals 0.33, right, as a decimal. Then it says, in a recent random sample of 2,300 adult Americans, 35% said they had never consumed alcohol. So you got this new study, right? A new study that said 35%. So then the question is, does this indicate that the current percentage of American adults who have never consumed alcohol is different from 33%? Now here is something that we haven't seen yet. Different from. I mean, we've seen it in the homework, but we haven't. The example problems that we've seen We haven't done this yet. Remember, different from, a lot of times what we've seen is greater than or less than. This is different from. Different from, when you see that mathematically, that's like saying not equal to, right? So this is going to be actually a two-tailed test. And it tells us to use a 5% level of significance, so that's our alpha level. So to get started here, they want us to state the null and the alternate hypothesis. So here is the null hypothesis is that, whoops, we want blue here. The null hypothesis is that P equals 0.33, or if you prefer 33%. But that's because they said right up here, suppose that this result is true, right? 33%. So we're going to assume that that's true. That's our null hypothesis. But then it says, you know, based on this study, is the current percentage of American adults who have never consumed alcohol different from 33%? Different from means that our alternate hypothesis is going to be that P is not equal to 0.33. So looking at this is a two-tailed test. I need to mention something because there's something that happens with this example, and that is sometimes I always use this example for section 8.3, and then what happens is on any test or quiz question, whenever a test of a population proportion comes up, students automatically think it's a two-tailed test. Okay. That is like completely missing what we're doing here. It's two-tailed because this right here says different from. Not because it's a proportion, it's because this says different from. That makes it not equal to. That's why it's a two-tailed test. So every time you see a proportion, question about proportions, don't think it's a two-tailed test. It's only two-tailed if it says different from. And it can be a two-tailed test or a test of the mean also. If you do the homework problems, you'll be okay with this because there's two-tailed tests in 8.1 and 8.2 also. But the key is it says different from, so that's why we have not equal to, and that's why it's a two-tailed test. So again, remember that P, that's the population proportion, right? Population proportion. So we have to kind of keep that in mind. We're always testing the population proportion. Just like before, we were testing the population mean, mu, right? So it's never going to be X bar here or here, and it's never going to be P hat here or here. It's always going to be either mu or P. And in this case, with proportions, it's P, population proportion. So which sampling distribution will you use and why? Well, this is a proportion, right? We're testing proportions. So it's going to be the normal distribution. So in Chapter 8, whenever you're asked this question, which sampling distribution will you use? There's only two answers in Chapter 8. It's either the normal distribution or student's t. And the only time it's student's t, if you remember, is when we're testing the mean and we don't know sigma. Whenever there's a proportion question involved, it's always standard normal distribution. Actually, I should probably make this a little better. Let's say standard normal distribution. So basically we're going to use z-scores, right? Now the reason I can do that is really I have to show that we really have to show we can do that. So n times p. Well, n is 2,300 because if you look at the question, it says in a recent random sample of 2,300 adult Americans. Okay, so 2,300 is n. And then P is a number given in the null hypothesis, which is 0.33. If you multiply these two together, you get 759, which is definitely bigger than 5. So we can say, okay, so that checks. N times Q, N again is 2,300. Well, if P is 0.33, Q is 0.67. Right? Because remember, P plus Q have to equal 1. So whatever P is, Q is 1 minus that. Right? So that's just from P plus Q equals 1, which means that Q equals 1 minus P. And if we multiply these two together, we're definitely going to get a number bigger than 5. So that checks. So remember, what we're checking is NP greater than 5 and NQ greater than 5. It's just like before when we were testing the mean and we would say, is the sample size 30 or more? This is the same sort of thing. So because of that, because these both work, we have what's called a large sample, and so we can go ahead and use the standard normal distribution. So then we have to use the sample data to compute the sample test statistic. So we've got, it says that we have this recent random sample of 2,300 adult Americans, and 35% said they had never consumed alcohol. So that is our p hat. Our p hat is 0.35. So to compute the test statistic, or the standardized test statistic, to find our z-score, we use our new formula, p hat minus p over p times q over n, all under the radical. So p hat is 0.35. And remember that p is the number in the null hypothesis, which is 0.33. So you go minus 0.33. And then we've got p times q. Well, remember, whatever this is the same, right? This is both p from the null hypothesis. So this will be 0.33 times 0.67. Because remember, q is always 1 take away p. So these two will always add up to 1. And of course, we need to multiply those two together, divide by n. And n, it says, is 2,300, right? Because it says in a recent random sample of 2,300 adult Americans, and we take the square root here. So as far as order of operation, just make sure you figure out that before you hit divided by. If you just type this minus that divided by, it's only going to divide this by whatever follows. So make sure you do this first. Put parentheses, or do this, hit enter, then hit divided by, so that we get order of operations taken care of. And if everything works out, you should get right around 2.04, which is a z-score again. So we can kind of estimate, in our mind a little bit, the p-value based on this z-score. Although this is two-tailed test, so this will be a little different. But then to find the p-value of the test statistic, for this one I'm going to draw this out because it's a two-tailed test. So we know we've got a z-score of 2.04. So if I draw this out, this is just standard normal curve, right? This is just a standard normal curve here. We've got 2.04. But we've also got negative 2.04 because this is a two-tailed test. So maybe I should have done this. Okay, here's 1, 2, 3. This is just a little bit beyond the 2. So here's 1, 2, 3. Negative 1, in other words, and negative 3. So the p-value, remember, is the area under the curve. So in this case, you've got, this is half of the p-value, here's the other half. So the way we figure out the p-value is we find one of these, then we double it. Right? So the p-value is going to be, I'm going to leave a little space and write probability that z is greater than or equal to 2.04, but I need to go 2 times that. 2 times that, because this z greater than or equal to 2.04 gives us this part, right? I need to also get this part. So because it's a two-tailed test, we need to double what we get. So this will give us equals, I'll put the 2 again, times normal CDF, 2.04 comma 10, right? Because we're going to find this area, then double it because we've got the p-value on both sides. And once we do that, that will give us right around 0.04. So you've got about 0.04. In other words, this over here is 0.02. This is also 0.02. You can see my picture's not really the greatest because mine has too much. The shaded areas, reality is a lot less area than what it shows in my picture. But I want to make sure everybody understands the 2 here is because this is a two-tailed test and it all comes down to the way they asked the question, because they said, does this indicate that the current percentage of American adults who have never consumed alcohol is different from? Different from means not equal to. And when you have a not equal in your alternate hypothesis, it basically means you have a two-tailed test. So we've got our p-value. And then we've got to take that p-value and do what we do every time, compare it to alpha, the level of significance. So for number 5, we go, okay, the p-value is equal to 0.04. Our alpha is 0.05. So we put a little box here. And we look at the p-value. We compare it to alpha. We see the p-value is less than alpha. And we know that whenever the p-value is less than alpha, we reject the null hypothesis. So we are going to reject the null hypothesis H0. And the book would say the data are statistically significant because whenever we reject the null hypothesis, by definition, the data are statistically significant. So it always, just like before, it comes down to looking at the p-value that we got, 0.04, comparing it to alpha, right, our original alpha, 0.05, and since this is less than that, remember what this means. Alpha says we're going to take a sample, and if that sample has a 5% chance or less of happening, then we're going to reject the null hypothesis. And that's what happened. It had only a 4% chance. So then we are ready to state the conclusion. So we always have to start off mentioning what our level of significance was. And this problem makes it really clear why. So I'm going to say at the 5% level of significance, comma. Now look what happened though here. If this had been a 0.01, then 0.04 would be greater than that, and we would not have rejected H0. We would get a completely opposite conclusion, right? That's why it's important to mention this. If we don't mention this, we're leaving off a lot of information. So we're mentioning at the 5% level of significance, mentioning, and then we'll tell what our conclusion is. But if alpha were 0.01 and we said at the 1% level of significance, we get the exact opposite conclusion. So that's why we have to mention this. That's why I mention it every time. So at the 5% level of significance, again, I'm going to use the same format as always. I'm going to say the sample data or evidence, because again, our sample data, that is our evidence. The sample data suggests that, okay, now look what I'm going to say. We rejected H0, which means we're going with H1, right? So suggest that, I'm going to write H1, but in words. So if you look at our H1 says P is not equal to 0.33. Now I'm just going to put that in words. And I'm going to write suggest that the current percentage of American adults who have never consumed alcohol is different from 33%. And that wording, I'm getting that right from the question. Look at the question they say. They say, does this indicate that the current percentage of American adults who have never consumed alcohol is different from 33%? And we're kind of saying yes, right? We're going with that. We're going with the alternate hypothesis. So the wording I'm getting here is just from their question. So I'm just going to use the same wording. I'm going to say, the sample data suggests that the current percentage of American adults who have never consumed alcohol is different from 33%. And when we say this, something we should probably point out here, this current percentage, that's really the population proportion, right? That's really P, population proportion. So they just worded it a little different than what we normally see. But that's what they mean. So when they say the current percentage, they're talking about the true percentage, the current percentage, the population proportion. So that one gives us an example of the kind of problems you run into 8.3. So give them a try, and remember the homework is super important. We got to get used to these kind of problems. So keep right on top of the homework. I know we're getting to the end of the semester, but don't let your foot off the gas yet. We're not quite there. We're close. So keep doing the homework and keep asking me questions.